Hello friends, I welcome you on my channel Engineering Mathematics djganit. In this lecture, we are going to discuss some more examples on Gauss elimination method. In previous two lectures, we have discussed Gauss elimination method for solving system of linear equations, and we have discussed how to write down the infinite number of solutions if they exist. And also we have discussed that if in row echelon form of the augmented matrix we obtain this type of row, all the entries are 0 except last entry. If there exists a row of this form where last entry is non-zero and all other entries are 0, then system has no solution. Also, we have discussed the meaning of leading and free variables. So, if all the variables become leading variables, or if there is no free variable, system has unique solution, and system has infinite number of solutions if there exists at least one free variable. So, with this in mind, we consider some more examples on Gauss elimination method. So, we consider this system. Here A, B, C are unknown quantities, and we have to find out values of A, B, C which satisfy this system. So, as usual, we have to write with the augmented matrix for given system. So, here first column corresponds to coefficients of A, second column corresponds to coefficients of B, and third column corresponds to coefficients of C. So, we can see here there is no A in the first equation. So, we consider coefficient of A to be 0. Second row has coefficient of 3 and here 6. So, first column is 0, 3, 6. Second column coefficients of B which are -2, 6 and 6. And third column coefficients of C 3, -3, 3. And last column corresponds to constants on the right hand side. Now we have to write down, or we have to convert this augmented matrix into row echelon form. So we can see here the first non-zero entry of second row is not to the right of the first non-zero entry of first row. So we have to interchange first row either with second or third row. So here we interchange first and second rows. So this second row is written in place of first row and first row is written in place of second row. Now this is the first non-zero entry of first row. So we must have this entry 0. So using this entry we make this entry 0. So for that we have to apply this entry with -2 and add here. So the required elementary row operation is multiplying first row by -2 and add in third row. So we apply this operation. R1 is multiplied with -2 added in third row. So third row will change. We have written first and second rows as it is. Now here we multiply this entry by -2, that is we obtain 3 into -2 which is 6 plus 6, so 0, then 6 into -2, that is -12 plus 6 which is -6, -3 into -2 which is 6 and plus 3, so we obtain 9. Similarly -2 into -2, 4 and plus 5 which is 9. So this is the first non-zero entry of first row. All the entries below this are 0. Now we come to the first non-zero entry of second row. So we have to make this 0. So we have to multiply this -2 with -3. So we obtain 6 here, and if we add 6 here we obtain 0. So next operation is multiplying second row with -3 and add in third row. So only third row will change. First two rows are written as it is. Here we have to multiply second row by minus 3 and add here. So 0 into minus 3 plus 0, which is 0. Minus 2 into minus 3, which is 6, and minus 6. 3 into minus 3, which is minus 9 plus 9, so we obtain 0. And 1 into minus 3, that is minus 3 plus 9, which is 6. So this is in row echelon form. And we can observe that the last row is in this form. Last entry is non-zero and all the other entries are 0. So this system has no solution. From the last row we can write 0 into A plus 0 into B plus 0 into C equal to 6. So therefore 0 equal to 6, which is not possible. So therefore given system has no solution, or given system is inconsistent. So as we have discussed, if we have this type of row in row echelon form, last entry is non-zero and all other entries are 0, then system has no solution. So here the last row is in this form. We can see last entry is 6, which is non-zero, and all other entries are 0. Therefore this system has no solution. We consider one more example. Given system is system of 3 linear equations in 3 variables x, y and z. We have to solve this by Gauss elimination and back substitution. So as usual we write down the augmented matrix for given system. First column corresponds to coefficients of x, which are 1, 2, 3. Second column corresponds to coefficients of y, which are 1, 4, 6. Third column corresponds to coefficients of z, which are 2, minus 3 and minus 5. And last column corresponds to constants on the right hand side, which are 9, 1, 0. So we start with first non-zero entry of first row. So we have to make these two 0. So to make this 0, we have to multiply first row by minus 2 and add in second row. Similarly, to make this 0, we multiply first row by minus 3 and add in third row. So required operations are multiplying first row by minus 2 and adding in second row, multiplying first row by minus 3 and adding in third row. So first row remains as it is, 1, 1, 2, 9, and here we multiply first row by minus 2 and add here. So minus 2 plus 2, 0, minus 2 plus 4, which is 2, 2 into minus 2, which is minus 4, and minus 3, which is minus 7, 9 into minus 2, which is minus 18, plus 1, so we have minus 17. Similarly, multiplying first row by minus 3, that is minus 3 plus 3, 0, minus 3 plus 6, which is 3, 2 into minus 3, which is minus 6, and minus 5, which is minus 11, 9 into minus 3, minus 27. So now this is the first non-zero entry of first row, and entries below this are 0. Now we come to the first non-zero entry of second row, so we must have 0 here. So to make this 0, we multiply or we divide by 2 and we multiply with negative of 3, that is minus 3 by 2. So next operation is multiplying second row with minus 3 by 2 and add in third row. So that we have written here. So only third row will change. We have written first and second rows as it is. Now we multiply second row by minus 3 by 2, that is 0 into minus 3 by 2 plus 0, then 2 into minus 3 by 2, which is minus 3, and plus 3, so 0. Then minus 7 into minus 3 by 2 and minus 11, that is 21 by 2 minus 11, which is 21 minus 22 by 2. So we obtain minus 1 by 2. Similarly, minus 17 is multiplied with minus 3 by 2 and added in minus 27. So this is 51 by 2 minus 54, 51 by 2 minus 27. So this is now 51 minus 54 divided by 2. So we obtain minus 3 by 2 here. So now we can see the first non-zero entry of each row is to the right of the first non-zero entry of its preceding row. So this is in row echelon form. And this column corresponds to x, this for y, and this for z. Now here we can see there is no row in this form. In the row echelon form, there is no row in this form. Therefore, this given system has a solution. Now we decide the leading variables. Here the first non-zero entry of first row corresponds to x. The first non-zero entry of second row corresponds to y, and the first non-zero entry of third row corresponds to z. So that means x, y, z are leading variables. That means all the variables become leading, or we can say that there is no free variable. So as we know, if there is no free variable, solution is unique. So, and we can write down the solution by solving the system corresponding to row echelon form. So because all the variables become leading variable, or there is no free variable, given system has unique solution. So we write down the system corresponding to row echelon form, which is 1 into x plus y plus 2z equal to 9, 0 into x, which is 0, plus 2y minus 7z equal to minus 17. And from last row, 0 into x plus 0 into y minus 1 by 2 into z, which is minus z by 2 equal to minus 3 by 2. Now we solve this system starting from last equation. So first we find out value of z, then we will put value of z in equation 2, and then putting values of y and z in equation 1, we obtain value of x. So this method is known as, or this process is known as back substitution. So now we find out values of x, y, z. So we can see from last equation we obtain z equal to 3. Then we put z equal to 3 in equation 2. So 2y minus 7 into z, that is 3, equal to minus 17. Therefore 2y minus 21 equal to minus 17. Therefore 2y is 21 minus 17, which is 4. Therefore y is 2. And then we put values of y and z in equation 1. So equation 1 is x plus y, y is 2, and plus 2z, 2 into value of z, which is 3, equal to 9. So after solving this, we obtain x equal to 1. So this is the solution of given system: x equal to 1, y equal to 2, z equal to 3, and solution is unique. Next example, solve the given system by Gauss elimination method. Here given system has 6 variables: x1, x2, x3, x1, x2, x3, x4, x5 and x6. So this is system of 4 linear equations in 6 variables. and we have to find out values of these 6 variables which satisfy each equation of the system. So we start with augmented matrix for the given system. First column corresponds to coefficients of x1 which are 1, 2, there is no x1 here, so we consider 0 and 2. So coefficients of x1 are 1, 2, 0, 2, that is first column. Second column corresponds to coefficients of x2 which are 3, 6, there is no x2 here, so we write 0 x2. So 3, 6, 0, 6, 3, 6, 0, 6. Third column for coefficients of x3 which are -2, -5, 5 and no x3 here, so we put 0. Similarly, there is no x4 here, so here in first row coefficients of x4 is 0. In second row coefficient of x4 is -2. Here it is 10 and 8. Similarly, coefficients of x5 are 2, 4, 2, 4 from first and second row. There is no x5 in third row, so we put 0. And here coefficient of x5 is 4. Coefficients of x6, there is no x6 in first row, so we put 0. Here -3, here 15 and then 18. And the constants on the right hand side are 0, -1, 5 and 6. So now we start with the first non-zero entry of first row. So we require this to be 0. So for that we multiply first row by -2 and add in second row, and same operation multiplying first row by -2 and adding in fourth row. So second and fourth row will change. First row is written as it is, third row is also written as it is. Now we check what about second row. So we multiply first row by -2. So -2 plus 2, 0. 3 into -2 which is -6 and plus 6, so it is 0. -2 into -2 which is 4, -5 which is -1. 0 into -2, 0 and plus -2, that is -2. 2 into -2 which is -4 plus 4, so 0. Then these two are 0, so if we multiply with -2 they will remain 0, so we have -3, -1 as it is. Now we check for second row. We have to multiply first row by -2 and add in fourth row. So -2 plus 2, 0. 3 into -2, -6 and plus 6, 0. -2 into -2 which is 4 plus 0, so we have 4. 0 into -2, 0 plus 8, so 8. 2 into -2 which is -4 and plus 4 which is 0, and these two are 0, so we have 18 and 6 as it is. So this is the first non-zero entry of first row. All the entries below this are 0. Now we come to the first non-zero entry of second row. So we must have these two entries 0. So to make this entry 0, we multiply third row by 5, and to make this 0, we multiply third row by 4. So we have to write first and second row as it is. Third row will change. For that we multiply second row by 5. So these two are 0. So these two entries will remain as it is. -1 into 5 which is -5 plus 5. So we obtain 0. -2 into 5 which is -10 plus 10. So we obtain 0. Here both are 0, so 0. -3 into 5 which is -15 plus 15, 0. -1 into 5 which is -5 and plus 5, so we obtain 0. Similarly, we multiply second row by 4 and add in fourth row. So these two are 0. So first two entries 0. Then minus 1 into 4, which is minus 4 plus 4. So we have 0. Minus 2 into 4, which is minus 8 plus 8. So 0. 0 into 4, which is 0 plus 0. Minus 3 into 4, which is minus 12 plus 18. So 16. Minus 1 into 4, which is minus 4 plus 6, which is 2. So this is the first non-zero entry of first row. All the entries below this are 0. First non-zero entry of second row. All the entries below this are 0. But we have 0 row in between. And for row echelon form, 0 row must be at the bottom of the matrix. So we interchange third and fourth row. So after interchanging third and fourth row, we can see given matrix is in row echelon form. The first non-zero entry of third row is to the right of the first non-zero entry of second row, and first non-zero entry of second row is to the right of the first non-zero entry of first row, and 0 row is at the bottom of the matrix. So this matrix is in row echelon form. Now we observe that there is no row of this form in this matrix. In this row echelon form, we don't have any row of this type. Therefore, given system has solution or given system is consistent. So for type of solution, we have to determine leading and free variables. So we know that this first column corresponds to x1, second for x2, third corresponds to x3, then x4, x5 and x6. Now if we concentrate on first non-zero entry of first row, then first non-zero entry of first row corresponds to the variable x1. So x1 is leading variable. First non-zero entry of second row corresponds to x3. So x3 is leading variable. And first non-zero entry of third row corresponds to x6. So x6 is leading variable. So here out of these 6 variables, x1, x3, x6 are leading variables, and x2, x4 and x5 are free variables. So we have free variable in the system. Therefore, given system has infinite number of solutions. Because we obtain a free variable, system has infinitely many solutions. So we have written here, which is in row echelon form with x1, x3, x6 as leading and x2, x4, x5 as free variables. So now we write down the system corresponding to this row echelon form, and then we convert leading variables in terms of free variables to write down the infinite number of solutions. So reduced system is 1 into x1, that is x1 plus 3x2 minus 2x3 plus 0x4, that is 0, plus 2x5 equal to 0. Second equation is 0x1 plus 0x2, that is 0. Then minus 1 into x3, so minus x3 minus 2x4 and minus 3x6 equal to minus 1. Third equation is, this corresponds to x6. All other variables become 0. 0 into x1 plus 0 into x2 up to x5. So third equation is 6 into x6 equal to 2. So now we start from equation 3, back substitution. So by equation 3 we obtain x6 equal to 1 by 3. So now we put value of x6 in equation 2. So we obtain minus x3 minus 2x4 minus 3 into x6, which is 1 by 3, equal to minus 1. So therefore minus x3 minus 2x4 minus 1 equal to minus 1. Now x3 is leading variable and x4 is free variable. So we express x3 in terms of x4. So here we have minus x3 equal to minus 1. This we consider on right hand side. So plus 2x4 plus 1, minus 1 will cancel out and 2x4. So because x3 is leading, we have expressed x3 in terms of free variable x4. Now in equation 1, we put x3 equal to minus 2x4. So equation 1 is x1 plus 3x2 minus 2x3. x3 is written as minus 2x4 plus 2x5 equal to 0. And we simplify this. This is x1 plus 3x2 plus 4x4 plus 2x5 equal to 0. And we have x2, x4, x5 as free variables. In this equation, x2, x4 and x5 are free variables and x1 is leading variable. So therefore we express x1 in terms of x2, x4, x5. So therefore x1 is written as minus 3x2 minus 4x4 minus 2x5. So here x1 is expressed in terms of free variables x2, x4, x5. Here x3 is expressed in terms of free variable x4. And x6 is leading variable, but its value is constant 1 by 3. So now we have expressed leading variables in terms of free variables. So next step is to assign arbitrary values to free variables. So we consider x2 equal to r, x4 equal to s, x5 equal to t, where r, s, t are any real numbers. And we express the solution in terms of r, s, t. So from this we have to put x2 equal to r, x4 equal to s, x5 equal to t. So we obtain x1 equal to minus 3r minus 4s minus 2t. Value of x2 is r, x3 is minus 2x4. So minus 2 into s. x4 is free variable, its value is s, x5 is t, and value of x6 is 1 by 3. Here r, s, t are any real variables. So for different values of r, s and t, we will have different values of x1, x2 up to x6. And r, s, t are any real numbers, therefore they can have infinite number of possible values. Therefore x1, x2, x3, x4, x5 and x6 also have infinite number of possible values. So this is the infinite number of solutions of given system, which are expressed in terms of free variable r, s and t. So in this way we can easily find out the solution of given system using Gauss elimination method. So I hope you like this lecture. In next lecture we will do some more examples on this Gauss elimination method. Thank you very much.